Good morning. Thanks to Steve and Tony for putting this workshop together. I would say over the last 2, maybe 3 weeks, I've been at 2 different meetings with Tony, and in each of the meetings he's come up to me and tried to talk me up about the workshop here. And the advice that he's been giving, he says, just don't give your regular research seminar. Really, there'll be a lot of students. You want to do a lot of background and tutorial material. But at the end of those warnings, every time he said, but of course, we'd like to hear some of the new stuff you've been working on. Okay, and so that's kind of a big ask. I'm going to try to do the best I can for giving you tutorial and background stuff, and at times we'll sort of drift into some of the more recent stuff. When I was at MIT, one of the revered elders had a nice phrase that sort of covered what it is we need to do today, and yeah. So it's better to uncover a little than to cover a lot. So we'll see how that goes. We're going to see how it plays out. Okay, so where to start? So we're going to start tutorial-wise and just talk a little bit about one of the basic ideas. Well, let me just go back a slide here. I guess what I mainly want to do is to tell you how to read what's going on in that title. So topological electronics and orbitronics. So electronics, we understand with that. Topological in this context needs a little bit of elaboration. We'll talk about how that goes. And orbitronics is something which is likely not familiar to many of you. And then we'll get to that towards the end. So a good place to start is with the concept of anomalous velocity, which is the thing that underlies most of what we're going to be doing this morning. And so what's the anomalous velocity? Well, you should understand that we're doing electrons in crystals. They're in bands. And you put fields on them, and they move. Okay, and so the equations of motion look like that. There's a forcing term which just comes from the fields. Here's the rate of change of the momentum. What's interesting is that when you look at the velocity, there's generically 2 pieces to it. And so roughly speaking, I would say the way to think about this is the first line is just classical mechanics. You got a particle, you put it's charged, it moves in a field. The second line is very much quantum mechanical. The fact that dE dk is not just sort of a simple velocity, but has the band structure encoded in it. Since the 30s, people know that you get backscattering on a lattice, and that will modify the dispersion relation. But the really interesting thing is the appearance of what's called the anomalous velocity, which is this last term here. It's a term which looks in the velocity like the dual to that magnetic deflection in the forcing term. Okay. And so that comes through this k dot cross omega term, and this omega is a kind of a curvature. We'll talk some more about this. And you can ask yourself, well, where does that come from? Why is it there? When does it appear? So here's a short explanation. Okay. So essentially it comes from the fact that an electron in a band is not a simple particle. It carries internal information, orbital and spin polarizations. These things generally change as the wave packet is moving from K point to K point. Okay? And so that's the origin of this term here. What has to happen as the packet is accelerated, it has to change its orbital or its spin polarization generically. Okay? And that shows up as a kind of phase. That phase can sometimes be eliminated if it's simply a gradient. It's trivial. One can simply redefine the phases and get rid of it. But sometimes you can't get rid of it. And so that's this idea here. Sometimes it comes from an unremovable k-dependence of some internal degree of freedom. Maybe it's orbital, maybe it's spin, maybe it's some combination. Okay? And when you have that, that term appears here, and that changes the motion. It's sort of the dual of the magnetic Lorentz deflection term here, but now it's acting directly on the velocity. So that's called the anomalous velocity. So when does it occur? Well, generically in a crystal, it'll require at least one of 2 things. Either you have to have broken time reversal symmetry in the crystal, in which case the deflection produced by this is a transverse deflection, which we call the anomalous Hall effect. So if you put a E field this way, you'll get a part of the current that goes sideways to it. Okay, and that comes from the anomalous velocity. So you can have that for sure. Or you can have it if you preserve T, but break inversion symmetry. That's the other possibility. Okay. Now the second one here is the one that we're going to be mostly focusing on, and this turns out to be harder to see. Okay, it's a Hall effect, but not the usual Hall effect for charge. Okay, and so, however, there's been great progress in mining this idea over the last 4 years, maybe a bit longer, looking for broken parity two-dimensional systems which actually show that effect. Okay, and so what do? Well, you can take graphene, you can make graphene into a bilayer and break parity by putting on a perpendicular electric field. Okay, that's one possibility. Or you can just take the ordinary TMDs that we know and heard about in the previous talk, like so. So these are both T-preserving systems. What generically happens is that because you're T invariant, you can't have a Hall effect. But you do have the anomalous, the anomalous velocity. And the way that shows up is that there's typically, compensating curvatures in various places in K-space, such that if you put on an E field, there's compensating currents. Okay, so no net charge current, but there is a thing called like a valley Hall current. If you were to assign the valleys a kind of a charge, what you would find is that there's a transverse motion of that charge in response to an E field in the plane. Okay, and this has been seen. Now, one thing you can do to actually turn this into a charge current, which is, to my mind, interesting to see that it works, but it's like a brute force approach to the problem, is if you could change the valley populations, you would actually turn this Hall current, the valley Hall current, into a charge Hall current, because you have more stuff moving in one direction than the other. And that's been done. So you can produce non-equilibrium states. There's various ways of doing that, and that's been shown quite beautifully. Now, that's not what I'm going to be telling you about this morning. That's the background. Here's background 3. What I'm going to tell you about is a way of doing this without changing the valley populations. Okay. Now, the notion is that what we can imagine doing is, instead of changing populations, we're going to try to exploit coherent control by optical fields to literally engineer the wave functions. Remember, the curvature comes from some particular behavior of the wave functions in space, and if you're clever enough, you can actually use optical fields to change them at will into a desired form. And our desired form will be to turn on anomalous response functions. And so that's the point. That's the new stuff. If we move fast enough at the end, we'll show you actually how that works. So the notion is that one can use optical control to basically tune the behavior of the block states. They're things that have internal structure, but that internal structure is tunable, okay, in principle. That will allow us to engineer the block K-space connections in a mathematical sense here. And that will turn what we'll call anomalous topological responses can be sort of brought on demand and switched. Turn the light off, it goes away. Turn it on, it goes on. Change the polarization, it goes on in some, in some different direction. It's really pretty powerful if this can be made to work. Now, I'll just summarize what's going to happen here. To do this, we're going to be doing low frequency responses by down-converting optical fields. That's the theory. I don't do experiments, by the way. I do the theory of this. This is the idea, but we think this can be done. This will make use of the frequency, phase, and polarization information of these fields. And it is nonlinear, which means you will need large intensities, but we've made estimates of the intensities. And then we'll do that at the very end, but the spoiler alert is this seems doable. I mean, this really is in the range of things that people can do with machines and devices that people can build now. They haven't done this yet, but I think one can do this. Okay, so I'm going to be switching back and forth from research mode to tutorial mode. Let me just sort of tell you some of the background for those ideas I was just telling you about. There's inspiration for this work, which was actually an experimental and theoretical paper that recently appeared, but it's been in preprint for a while. It involves this two-dimensional silicide. I'll tell you why that's interesting in a moment. That will give us a model that we're then going to study to show what's going on in that. And that will allow us to confront these optically controlled anomalous Hall effects. And then at the end, we'll talk about the optical control. Okay, so let me just briefly summarize what went on in that paper. Part of it was theory, part of it was experiment. This copper silicide is a two-dimensional material. It's basically it's copper. The copper is on a honeycomb, and the silicons like embed the honeycomb and bond into the copper network like so. And the DFT says if you make this thing freestanding, it'll be flat. Okay. It turns out that this stuff is made pretty easily. It's made if you try to grow silicon on copper. In that case, it's not quite clear it's flat, but if you get it off there, at least the theory says that it ought to be a flat thing. This paper actually reported some ARPEs on supported films of this, which agrees with what I'm going to show you in a moment. And the flatness is, well, you have to get it off the copper somehow. Okay, so here's the band structure. Okay, so here's the band structure for that system here. There are these dispersing bands here. This is without spin-orbit coupling. Here's with spin-orbit coupling. The thing to notice is that these are pretty much the same. Okay, and to show that the spin-orbit coupling is really in there, you can just turn it up artificially large, and you wind up producing these tiny gaps here. But for a realistic spin-orbit coupling, what you get is this. Now, the title of this paper was Discovery of Two-Dimensional Line Nodes. And what they were pointing to is the fact that when that thing is flat, what's going to happen is there's bands which are even and odd under mirror symmetry. When those things intersect, they intersect on lines because they can't mix because of the mirror symmetry. It's mirror symmetric. You can't mix the mirror even and mirror odd bands. You do a little bit when you put on spin orbit. That's because you can absorb it in the spin, basically. But it's a really weak effect. And so for all practical purposes, this is the same as that. Okay. So here's the model for that. So here's the network I was showing you as a moment ago. Now, it's pretty clear if you think about it that what goes on here is that you get these, silicons that are pretty well separated. The active orbitals on the silicons are the 3p orbitals, the two classes, the ones that are even and odd under the Z mirror symmetry. And the copper 3D bands are somewhere else. So what generically happens is that you get these interactions between silicons that are being mediated just by the copper 3D state. So there's going to be some interactions, some coupling between these silicons that comes from just integrating out that band there. So the natural model to think about is just get rid of that altogether. Okay? What you now have is a vector degree of freedom on each Bravais lattice site of a triangular lattice, and that's the physics that one wants to study. That'll describe the low energy physics. And it does. In fact, it does a lot more than was expected from that theory paper. So here's why, basically. So what you have is each vertex supports this vector-like degree of freedom. It's got a Z and two in-plane components. The hopping between neighbors is some matrix valued object, but it can't mix the mirror even and mirror odd subspaces, so it has a form like that. And the interesting thing is that the in-plane p degrees of freedom in this Cartesian basis, well, those depend on the direction of the hop. So as you move from site to site, there's some rotation in that 2x2 matrix. It's different in different directions, although formally it's the same thing. All you're doing is changing the direction of the hop. Now, it'll be useful in a moment to take this into an axial and angular momentum basis where we just transform this to the axial harmonics, if you like. And then here's the mirror odd thing over here, and the effect of this matrix is now distributed into these four terms that appear out here. Both of these are useful. I'm going to show you what happens with this first because it's a good lesson, and then we'll see really the physics comes out of this, out of this formulation here. Okay, so there's the model. We had this 3x3 matrix valued Hamiltonian written in that form in this Cartesian basis. You see that it really neatly parses into three pieces. One piece is really what in the jargon a scalar term. It's like the average dispersion over all three bands. I like to think about it as a k-dependent chemical potential because that's what it is. It's just like a scalar potential. This term here tells you that the mirror even and mirror odd spaces are different. That's the crystal field here. And having done that, the only remaining term is this vector term here. And how about that? This is some k-dependent magnetic field coupled to the orbital moment. That's where all the geometry is. The topology is in the last term. Okay? Take out the crystal field. Take out the chemical potential. There's some underlying quantum geometry in the fact that we have this term here, which is really just a k-dependent field coupled to the orbital angular momentum. Okay, so we're going to be focusing on that. First of all, what you can say is that this is really very much unlike graphene, our other favorite two-dimensional material, in that each Bravais lattice site has bonds in apodal directions, both forward and backward directions. And that means that this matrix here, it's got to be purely real. The y component of that thing has got to be 0. Good, okay. Now this is what we had found before, is that the mirror even and mirror odd subspaces, they intersect. Those are line nodes, okay. And now you can ask yourself, are there other nodes? Are there other places where the bands come into contact in that problem? Or is it just the line nodes? And that's where this gets pretty interesting. So, tutorial, okay. Are there other two-fold degeneracies contacts and other means besides the line nodes that are enforced by mirror symmetry? Is that possible or not? And so here's a very interesting argument. This goes back to sort of a Wigner-type argument. It has to do with level crossings and level repulsions. You just ask yourself, if bands are going to cross through each other, then there's some sort of effective treatment in terms of those two bands, which would have this form for a Hermitian Hamiltonian. Okay. And so the energy, this is three anti-commuting terms. The energies are the sums of the squares of those coefficients. Okay, that's three things have to be brought to zero for the things to actually cross. Okay. However, there's a constraint. The constraint was that we were on a Bravais lattice, so you can't have an HY. Okay. 2 degrees of freedom. Okay. So we've got two terms, and there's two momenta. Okay. Which means you can generically tune. You can find a place where there's two real functions tuned by two real momenta such that they simultaneously vanish. That's quite possible. But if it occurs, it will occur only at points. Okay. Because it's a special solution. And those points are given names depending on who you are. You might call them exceptional points. Some people call them diabolical points. Some people call them vial points. Okay. But the point is, they're just points. Okay. So you have the lines that were expected, and there are these points which generically they have to occur, and they're actually pretty important. Okay. And so it's not mysterious where they occur on this particular lattice. Here's the band structure in that model. This thing here, there's actually two line nodes. That's one of them here. The bands intersect twice. There's one other one up here. I didn't put a red circle for it. But here's the points, and they're points. They occur at the K point, the K prime point is time reversed here. They also occur here at the zone center. Those are all points of threefold symmetry where there should be twofold degeneracies, and indeed there are. Okay, now, more tutorial, more on diabolical points. Why are we interested in point? These things occupy almost no phase space. It's only a point, for God's sake. Okay, why is this interesting? Well, the reason it's interesting is that once they're in there, you can't get rid of them. Okay, they're unremovable. If they're in there, you can't make a perturbative change to the Hamiltonian and get rid of them. Okay. Now, yeah, so cannot be removed perturbatively. That's an important word. I put that in bold, but you can't. If you try to break like the threefold symmetry and say, well, that will screw it up because you're not going to have the zone corner point over there, what will happen is the twofold crossing remains. It just moves a little bit off the threefold point. Okay, you can't get rid of it. The only way of doing it is to have it find what's like its antiparticle. 2 points of different twist can meet and annihilate. But that's not a perturbative effect. You got to move them around a big distance in the zone. So once they're in there, they're in there. You got to deal with them. The other interesting point is that whenever you have that, the band eigenstates that we were talking about have these internal polarizations that are twisting in a singular manner around that point. Okay. So the internal polarization is changing in a very fast way, and that means that the curvature I was talking about on the first tutorial slide is generically really large. Okay, and that means if you're looking for anomalous responses, this is the place to look. Okay, it's where not only is there an allowed response, it will be exceptionally large. Okay, so, and finally, I included in this list, I don't quite know how to pronounce them, okay, or much less it's plural. Okay, but they're sort of interesting to look at. Okay, so if you're mathematically inclined, you would say that that's really a reason for studying these things. So depending on your orientation, this might be first in the list. I put it at the bottom because we're all materials guys. Although Mitch didn't make it, I was going to make a joke about to Mitch Luskin about this, but nonetheless, okay. So he's a mathematical colleague of ours. So okay, let's learn some more about diabolical points. Let me do this instead in an axial basis, and here you learn something really quite profound about this. In the axial basis, instead of having, well, this is the form. We're still in this 2x2 matrix. Now it's the off-diagonal terms that are non-zero. These things are generically complex. The axial basis has a complex character to it. The symmetry was requiring that this diagonal term be zero now. That used to be the y term, now it's the z term. Any term that would be here would violate basically PT. So in 2 dimensions, TC2. Okay. And again, C3 requires the twofold contacts at gamma and K. And here's the counting rules. So we're talking about P-like degrees of freedom. These off-diagonal terms are going to zero at these special points. But now what has to happen as you move away from these points is we're trying to connect states that are different by 2 units of angular momentum. This is fundamentally unlike graphene. In graphene, that number is 1. Okay. If it's 1, it means that that degeneracy is actually broken to linear order in the momentum around that point. Okay. But here it's 2. Okay. Now, at the zone center, when you mean like you're on a crystal, when you just mean 2, you mean 2 mod 6. Okay. But 2 mod 6 is 2. Okay. It means quadratic dispersion around the zone center. The zone corner, 2, is you really have threefold symmetry. It's 2 mod 3. 2 mod 3 is 1. Okay. That means there'll be linear dispersion around the corners and quadratic dispersion around the center. And that is a huge insight about how this works. Generically, for these 2 points, there'll be a quadratic dispersion around the center and linear dispersion around the corners. And we can actually see that if you look carefully, that's what you see. Yeah, quadratic here, linear here on the corners. And if you look at the phase of that complex number, that tells you exactly how this works. Namely, the k and the k prime points, this is the phase of that term. Notice that it twists around the full 2 pi, around k and k prime, but with the same sense of twist. Look at the color wheel. It goes blue, yellow here counterclockwise. Same thing here, blue counterclockwise. There's a rule that means the total twist in the zone has to be 0. So 2 counterclockwise have to be canceled by a 2 clockwise somewhere. And that 2 clockwise is the thing that occurred at the zone center. Notice that it goes in the other direction and is twice as large. Okay. So this is unlike people here who study graphene, you encounter a version of this which is way simpler. There, it turns out that the way it works is the 2 k points carry opposite twists. Okay. Here, it's the same twist in the corner, canceled by a compensating twist somewhere else. And so to compare them directly, I think this is one of the, if you only retain a few things besides the tutorial from this talk, this is the slide to keep in your head. Okay. This is the phase profile for the thing that mixes those two bands. For graphene, is this famous thing where you get these sort of particle and antiparticle in the 2 corners. Okay, and there's a branch cut in that thing which connects these two. Here, in this j equal to minus 1, 2 situation, the branch cut connects both of the corners to the center. Okay, so topologically it's a different thing. All the corners have the same twist. The center has a different twist that'll cancel it. Yeah, and so let's go one slide ahead. So here's one of the functional consequences of that. In graphene, these 2 points, they occur at time reverse points, therefore the energies have to be the same. So those 2 twists not only have different twists, but they occur at the same energy. In this lattice here, here's the k points. Is minus once, twice is minus 2. Here's the compensating thing at gamma. But there's no symmetry that relates gamma to k, which means that generally those things will occur at different energies. So if you're in the business of trying to isolate some sort of direct singularity, Weyl singularity, with some net sense of handedness, this is the perfect place to look, because they're already at different places in energy. You don't have to tune them out of resonance. They're in there automatically. Okay. Okay. So we're coming back to some more tutorial stuff in a moment. At the moment, I should say that we're now interested in looking for functional behavior associated with this. And it's good to look, are there precedents in things that we already know about? And there's some loose precedents. We know about things that are called MultiVial points. These occur in 3-dimensional materials. They typically involve double winding and then linear dispersion in a third direction. That can occur along a rotational symmetry axis, as it turns out. But that's not, here we have 2D, so there's not really a third component of the momentum. What is going to happen is that this will be converted into some control parameter, which will be able to break that. Okay. So in bilayer graphene, something similar happens. There are these quadratic degeneracies in the Bernal bilayer broken by this interlayer potential. This is quite different here because the Z mirror is going to involve this vector value thing that connects the mirror even and mirror odd space. It's a very different object. So looking around for precedents, I also like to point out there's even a precedent in botany. Okay, so what's the precedent in botany? Well, there's a definition of botany that I heard a long time ago that I sort of keep in my toolbox. Okay, botany is the science in which plants are known by their aliases. In other words, what you do is you define things by what they are not. Okay, that's one of the ways of thinking about botany. And that's not what we're doing here either. Okay, so the first 2 precedents are not exactly what we're going to do, and we're not going to be just classifying nodes for the sake of nodes. We want to know what they do. When you have that, what can you do with that kind of a texture? Okay, so Okay, so here we go. So how does it work? Well, what we'll do is we'll gap out those point nodes, and what that will do is take the Berry curvature, and instead of having it at a point, what it will generally do is, is distributed, okay, around those nodes. That's known. As it happens on the honeycomb and its heteropolar variance, this will only show up in transport if you have a way of breaking the valley symmetry. Okay. In other words, like the mass term you have to generate automatically has to be different in the two valleys. Reason? The two nodes you're trying to gap out already have different twists. So if you put on the same mass, the whole effect is going to integrate to zero. Okay. And so there's ways of trying to make the mass different. And they're quite celebrated, I will say. I will tell you that they're all kind of weird. Okay, because what you're trying to do is produce a mass term which flips its sign in the two valleys that generically requires some sort of non-local coupling such that the k-dependence flips its sign in the two valleys. This is the basis for the Haldane model of the Chern insulator, and frankly, it's even the basis of, of what Charlie Kane and I wrote down a few years ago with spin to produce the quantum spin Hall state. It's a way of just making a mass which flips its sign. And really, that makes it challenging. It's hard to actually do that. There's been success, some success, of course, but it's not trivial. And so the two pictures are something like this. You can do it by producing some sort of weird second neighbor coupling which knows clockwise from anti-clockwise. That's a way of doing it. You can by hand change the valley populations. That's what I was starting with on the first slide. That's a way of getting around this sort of opposite mass threshold. Make sure that the masses maybe are the same, but different numbers of particles in the two valleys. Okay. Okay. Here, instead, the two valleys contain the same twist already. That means there's going to be topology when the mass has the same sign, is in the same sense in both valleys. That means it doesn't have to be non-local. In fact, the simplest things that one could imagine will actually do this. Okay, and here's a tutorial way of summarizing that. Okay, it is much simpler, and much is really much. I mean, almost anything you would write down, okay, in terms of a local coupling, will actually do this for you. And here are some examples. Okay, you can break T. It would be like putting on just an ordinary ferromagnet would do it. Okay, okay, no, the thing we'll talk about is putting on circularly polarized light. That will do it. Okay, there's other ways of doing it. There's a T-even tensor, which would be buckling, will do this here. And there's some more exotic states here, which involve non-collinear spin states. There's just various ways of producing, potentials that'll be the same in the two valleys that will have some sort of topological anomalous transport associated with them. That's the one we'll talk about. Okay, so what we'll do first is talk about a charge Hall conductance. And here's a way of formulating that. This is the thing that I was calling omega in one of the earlier slides here. You basically integrate this thing over the occupied states. That will give you the antisymmetric off-diagonal conductance, the Hall conductance. Here's the definitions of those various terms. Okay, and so here's the bands. These are the bands we had. We're put on a potential which does this. It's just like an on-site mass term, basically. And what it does is it opens up those things that we're touching are no longer touching. Both the quadratic touching here has been relieved. The linear touching here is also relieved. The line nodes are still there because this potential preserves that symmetry. Okay, but you wind up gapping these things. These gaps are guaranteed to be topological now. Okay, so and we'll compute some things. Oh, there's the Berry curvature associated. This is a really informative graph. So what I'm doing here in this density plot is giving you a map in the color scale of where the curvature is large and where it's not so large and where it's even negative. So here you get that around the corners, which is where where we were gapping it, there's a very large curvature around those points. Okay. Had you done this for the honeycomb lattice, what will happen is that these guys here change their signs in a threefold symmetric pattern, such that if the population of all the valleys is the same, this thing integrates to zero. Okay, but here it doesn't integrate to zero. Okay, because all the terms have the same sign. That integrates to something. And what's the something? Well, here it is. So what I'm doing here is we're just taking the chemical potential and marching it through that band. Okay, and what happens is that indeed there's a Hall conductance here in the natural units. It turns out that it increases, like you might say that it's like electron light down here. This plateau is when you're in one of those gaps. Okay. And it turns around, goes to be like Hall-like over here, and finally returns to zero. So what's happening here is that you're basically beating the negative twist in the corners, if you like, against the positive twist at the center, and they compete but you can find places where one or the other dominates. Okay, oh, sorry.
Just adding.
Okay, okay. You can make that potential, we're just making a model now. You can make it so strong that the entire system gets gapped. There, okay. If you do that, there's a theorem that says that the Hall conductance has to be integer quantized. Okay. So what's the integer? Well, when you fully gap it like this, what happens is that you have optimum interference of the -1 and +2 points. And so what happens to the Hall conductance? It's 0. Okay. It's quantized to 0. The system is T-broken, but there's no net Chern number in this manifold here. If you have a Fermi surface here, there'll be a Hall conductance, but it actually is 0, perfectly compensated in this gap. Okay. So we'll talk some more about how that shows up in a second. Okay. Good. Okay. Back to tutorial. How do you think about these anomalous responses? Should you think about it as a response in the bulk, as we're doing here, or something going on at the boundary? And so the answer is both, or either, depending on how you want to read that. So, but both are actually useful. Okay, you can view it as a bulk flow being produced by the anomalous velocity term that we started with. Okay, that's the anomalous Hall effect. Certainly that's the case with a Fermi surface in those bands. It turns out it doesn't even need a Fermi surface, okay, in which case you get a quantized version of the flow. That's the quantum anomalous Hall effect. But you can also view it as the effect of having extra modes on the boundary, which are one-way modes. So you have ballistic motion in the mode, and those modes are one-way, which means no turning around, which means no backscattering, which means no dissipation. Okay, so you get these special modes that can. Okay, and these two are actually, the same statement. These are dual to each other. These ones down here are just the quantum versions of the skipping orbits that we know from elementary electrodynamics. So, yeah, here's a tutorial. So I don't know if the slide shows up. Yeah, here's a picture of that. I cribbed this. I found this. This is a beautiful graphic. I found this off some lecture notes given to a high-energy physics audience, where the guy was talking about anomalies. Okay, and one of the things that he talked about was the quantum Hall effect. And it's, it is a beautifully drawn. I really like a very nice sketch of the phenomena. But basically, here's your medium here. There's some boundary out here. What goes on is that you get these cyclotron orbits in the bulk. Those are just orbits. They're localized things. Okay, but on the boundary, what will happen is those orbits will hit the boundary. And if they hit the boundary, they skip, and they run tangent to the boundary, and those are the skipping orbits in classical physics. Okay, and so you can view that in many ways. One is just the effect of this Lorentz force, or you move to a drift frame where the effect of the electric field is being balanced by the effect of the magnetic deflection. So you can ask yourself, in terms of the response I was just showing you, what's the edge state picture? Does it have one? Yes. So here's a model. That's our triangular lattice. It's going to be a ribbon which will go infinitely left to right. Nice crystal. Momentum is going to be quantized along the horizontal direction, conserved along the horizontal direction. Okay, so here's the bands. Now, this dense stuff here, these are where the bulk bands project up into the surface as a function of kx. You can have surface modes in in these windows, in the open regions here. And indeed they occur. There are pairs of them in each of these gaps. This one is moving to the right, that one's moving to the left. They're color-coded, and the color code tells you which boundary they're sitting on. Okay, so this one over here in that gap is actually a ballistic mode which goes right. And this one here is a ballistic mode that goes left. Okay. So what you do is you set a chemical potential, okay, in that little gap region here, and the plateau we were seeing was the propagation in that green band. Okay. Now, it was not quantized. It didn't go to exactly E squared over H. The reason is that there's this parasitic bunch of bulk stuff that it's sitting on. Okay, here. Okay. And what that does is it essentially screens this. There's a kind of buried curvature of the opposite sense associated with that band. But as it happens, that curvature is very large up here at some remote energy and gets to be weak down at the energy. So the thing is not quantized to 1. As it turns out, the plateau is like 0.8. Okay. It's pretty good. Okay. And what else am I going to say about that? Yeah, and so actually here, this one here is not, it's 0.7. Okay. So here we are marching through the band. Here's the chemical potential in this little gap that appears here, and it's flattish, okay, like that. The change in this is basically a measure of the strength of the Berry curvature from this remote screening point down here in the range that we're studying. Okay, some more things about edge states. Oh yeah, so there's two important energy scales. One is what's the size of that gap. The other is what's the offset, which is basically a measure of the strength of the crystal field. So both things count. So if you were to take the gap parameter, for example, and flip its sign, you'd get the same picture except you'd just reverse the red and the blue colors. Okay, so you get the same thing but with currents reversed. If you change the crystal field, well, this actually changes a lot. And so here's the picture I was just showing you. Weak coupling, delta is going to be a lot less than the crystal field term. That's the thing we think is actually experimentally relevant, but as model building, you can do the other thing and make the crystal field term really small. Okay. What you get then is this. You also get the edge modes, but they don't traverse one singularity to the other. They're actually flattish, which means that there's a range in chemical potential where, in fact, there's no modes, which means there's no Hall conductance. And that's what we found. That's the strong coupling regime where the Hall effect is exactly quenched, okay, even though T is broken, okay. And if you think about it, what that means is that that lowest manifold, there's no Chern number associated with this set of bands. That means this thing can actually connect adiabatically to a trivial atomic insulator. And of course, that has to be the right answer because the perturbations we put on were local. There's no non-local entanglement here whatsoever. Okay? So it's got to be that in that regime, this thing is really just like having atoms, which it is. Okay? It's only in this regime here that you begin to notice that it's really coupled in some way. Okay, so I'm going to spend the last few minutes now talking about optical control. So that's what happens in this model. You put this vector degree of freedom on a lattice, you let it loose, you ask what happens, you discover that it looks really simple. It's not as simple as it looks. Okay, there's actually an interesting underlying geometry which says that you have this opportunity for isolating points of a given two-dimensional twist, which makes them easier to manipulate with accessible experimental fields. So we're going to do this optically now. Okay, so here's the idea. We're going to imagine imposing this kind of thing optically. So we're going to couple the electrons to circularly polarized light. The interaction term is, S is the sense of circular polarization. We'll talk a little bit more about how this works in detail in a moment, but generally what happens is that you integrate out the first bands shifted by one frequency of the photon here, and then you take what's left and you trace it against L sub z, which is the term that you want to break the symmetry with. So it's like having a Zeeman field, but it's being controlled by this optical degree of freedom. And what you discover is that it exists. It's odd in frequency, which it has to be. It goes to quadratic order in the fields, which means it's linear in intensity. And what is cool is that it actually has this resonant structure. Okay, there's omega and delta. And what is omega? So omega is the light. Delta's the crystal field. Okay. And that occurs because when you put on light on this system, it can only couple the in-plane modes to the out-of-plane degree of freedom. It's delta m's got to be 1. Okay? And that's an important feature of this problem. Just to remind you, if you try to do this in TMDs or graphene and stuff like that, there what you're doing is the two bands are different by 1 unit of angular momentum. So when you put on light, what will happen is that indeed you can produce terms which will gap out this crossing point. That's quite possible. But inevitably, you will also have excitation of charge carriers between these two bands. And that makes this tricky, because what you want to be doing is working in a regime where you can see the effect of the coherent mixing and not have it obscured by the fact that you've got a lot of carriers that are being generated. So you have to find the sweet spot where you've opened up the gap, but you haven't really blocked it by having a large population inversion here. Okay. Well, here you go. For our problem here, it's really spin 1. There are no direct transitions allowed between those, only remote couplings to some other band, which is at some different energy. Okay? That means you're going to generate terms that coherently mix and open up this gap, and no free carriers at low energy. So you'll be able to see it immediately, assuming you can produce a perturbation big enough to actually gap that system out. So one of the main stumbling blocks here is going to be avoided completely over here immediately. Okay, so now for some plug and chug. Okay, so you can do that. This is a formula one writes down in a flow-K theory. This is sometimes called a flow-K Magnus expansion, which is the appropriate way to think about this when you're looking to low order in the optical fields. And so in the 2x2 space, it has this form here. You trace it against the appropriate form, and so here it is. This is the term that corresponds to little delta, and now we know what all these things are. So alpha is some matrix element, typically the size of the atom or the cell. That's the light intensity here. odd in frequency, C. There are these energy denominators. So we can estimate what you need to do to actually make this work. Okay, so let's suppose you want to be generous about this and make the optically induced gap 100 millivolts. Okay, that's a pretty big ask, but suppose you want to really think big. Well, that would require a field intensity of like 10 to the 8th or 10 to the 9th volts, depending if you're on or off volts per meter, okay, depending if you're on or off resonance. Okay, if you're on, it's the lower. If you're off, it'll be the higher. Okay, something like that. And so resonance means resonance with that crystal field splitting. So is that possible? Well, I've listed here one, two, three, 4 papers, all of which are talking about experiments which are doing fields of exactly that scale. Okay. But one of these doesn't count because it's theory. Okay. Okay. So okay. So Angel noticed that if you took graphene and studied it and pumped it in the UV, I think it is, you can down convert it to a field which typically has that strength, which with reasonable values for the scattering times and so forth. But these other ones are actually experiments. Okay, Keith Nelson, Aaron Lindenberg, Everett. Okay, these guys are all. I think these have been demonstrated in some cases. Okay, so that's something something one can do. And I will point out that this is at 100 millivolts. I mean, in transport, this would show up for things like 100 times smaller. Okay, you can actually see this with even modest circularly polarized fields. That's pretty cool. Okay, so let's do something else. Okay, good. So can you do the same? Can you play the same trick, and take the vial point, diabolical point, and keep it as a point, but then tilt the cones? Okay, can you engineer the cones to actually do that? There's a lot of reasons for actually doing that, because it means if you could do that, you'd actually have a kind of a photogalvanic phenomena. You send in light, you excite between bands, then the states at k and minus k have different velocities, and you get a net current. Okay, so you can, if you could do this, this would be very useful because you would get a current just by exciting carriers, and we believe we have lots of control on the polarization of these fields. Okay. Okay, no. Okay, turns out no. Okay, at least we haven't discovered how to do it yet, but we know there's a general principle here. This is the flow no-go. It's just abbreviation for flow K can't do this. Okay. Okay, at least in the form that I told you. Okay. And there's a reason that there's a symmetry that connects the various points that prevents this from actually going on. Now, I do believe, by the way, you could get around this theorem if you could buckle at the same time you put on circularly polarized light. That could make this work, actually, but in the way that I've described it here, to be fair about it, it doesn't work. Okay, good. So I left off one of my topics, but I think maybe what I'll do is just close with a couple of things that are on our minds about this and just tell you about them. So we were motivated by this copper silicide. It turns out that this inspires the idea, but it's not the best place to look for it. The copper D bands make this pretty complicated, actually. I'm quite confident that with full band structure DFT, we would see these effects, but not in as clean a form as I've shown you, because some of these singularities overlap the D bands, and that makes it messy. So it would be useful to actually find, the model's quite generic, by the way, to find other material systems that have this physics embedded in them. And I'm optimistic you could do that because the model is quite generic. As a matter of fact, we happen to know that this kind of thinking has actually popped up in a few contexts already. A few years back, people were talking about topological bands on a honeycomb lattice in which the P states were not out of plane but in plane. Okay, and that has interesting geometry, and it's pretty much the stuff that I was telling you about here, except on a honeycomb. It's not triangular. But that's a rich subject. These are actually quite interesting papers. The other thing is, remarkably, people these days are actively discussing and arguing and trying to interpret what goes on in Mele graphene at small angles. These are effective models. There must be 6 of them out there from the theorists. No 2 of the 6 are the same. Okay, and people are discussing how to sort of sort this out. But it turns out that the generic model is really quite similar to this up here. It's a regular lattice in 2 dimensions set by the Mele with in-plane P degrees of freedom instead of out of plane. That's the basic structure of the theory. So the stuff we're learning here is going to be relevant for what's going on down here as well. Everything I did here had was without spin. If you put on spin, then you have some other opportunities, magnetism, spin orbit effects, et cetera. And here's one of the things that I left out because I wanted to make sure I got to the end of the talk here. But we also know that besides charge transport, there's a kind of transport coefficient having to do with a transverse coherent motion of the angular momentum, not charge. An angular momentum current is actually an interesting thing because it's T even, okay? And you can produce that kind of thing as it happens. And it has some interesting structure with two important differences. One is it doesn't have the edge state interpretation. It's a bulk response without edge states. And the reason is that when you transport angular momentum in the bulk, it goes out to the surface and scatters off the boundary, which is not symmetric any longer, and it gets converted, okay, at the boundary. So the observability of the effect has to do with how do you understand the scattering at the boundary, and that's still a pretty open issue for this kind of a problem. Okay, so I think that look at that. I'm exactly on. That's amazing. Okay. Anyway, that's the stuff that I wanted to tell you about, and I'll just pass it back to Tony. And thanks again, Tony, for putting this meeting together. Okay.
Thank you, Eugene.
Right.
Is that viewed from outside the material or inside the material? With the idea being from outside it's moving to the right, from inside it's moving to the left.
Well, I think then two proper observers would be, describing the same thing in different language. So the slope of that thing is, d energy dk, and in this reference frame here, you can see that's like a right-moving thing with positive slope. So I guess it is true that if you were on the outside of that, you would say that thing corresponds to a left-moving thing, but that's just because my right here is your left. Okay, that's the only difference, right? Okay, so, but it's the same physical current.
Sure.
Okay, so right.
Do you have a convention?
Yeah, I mean it has to do with the orientation of the normal, right? So like one could write it in a representation invariant way by understanding what the direction of the normal to the plane and normal to the interior of the material is. Okay, and those two things would then define what direction you mean. The third thing would be the sign of the gap that is producing that perturbation. So those three things taken together will give you an unambiguous description of the direction of motion.
So presumably by playing with your crystal, having more complex bases, instead of +2, you can
Yes.
+3, +4, whatever you want.
Absolutely, yeah.
In terms of the Floquet stuff, does it help to make the gaps bigger if you have +2, +3, +4, or is that?
I think the optimum thing for the Floquet is to tune this crystal field into the range of your optical frequency to make maximum use of that resonance. Okay, so I would say if you're like put D waves, okay, then but somewhere one hopes that there's going to be some combination which is going to have 2 minus 1, like there'll be a P wave somewhere else, and that's the term that's the Floquet state you have to couple through. So you shift by the frequency and you try to change the angular momentum by 1. What is the problem with the pseudo spin 1/2 problem is that the Floquet states are the states you're trying to coherently mix. So that's just a problem. I mean, you're going to produce real carriers at the same time that you're trying to coherently mix these states. So these higher angular momentum variants have a very nice, runaround end run around that. So that's what I think that will really be. Yeah.
So, Jim, one question. Can you comment on the spin splitting in this system and what you anticipate will be interesting in terms of the spin transport?
Yeah. So the comment is that we haven't really thought much about spin at all. And in fact, and deliberately not, because instead of having put on spin orbit here, then we're not really talking about an L equal to 1 manifold anymore. We're talking about a 3/2, for example. And so the short of it is that we know something different is going to happen. Okay. So, but the models that we've done so far have been spinless objects. Yeah.
All right. So with this, let's thank Professor Mele again.